Okay, here's another example. This is a rigid body pendulum with a horizontal force. What do we mean by this? So, actually, let me use the following. So here's a pendulum, so it can sort of pivot freely about this point, which let's call that O. Let's call this angle theta, and this length L. And let's say there's a force being applied on this pendulum at the endpoint, force F, like so. Let's say the center of mass, which is halfway, let's say, from here to here, is the point C. Let's call this point A, the end point. And that's about it. Okay, so that's the setup. And you're asked, find an expression for the angular acceleration alpha equals theta double dot, right? So that's really what we mean by angular acceleration in terms of mass m of the pendulum, length L, force F, G, acceleration due to gravity, which is downwards, and angle theta. Okay, so this is what we want to find. So an expression like this would be called equation of motion. Determine what's called the equation of motion, which is essentially an expression for the acceleration. Okay, in any case, so that's the question. Now, how do we approach this problem? As we've discussed, the two primary principles that we use are F equals ma and sum of moments equals I alpha, and their various generalizations or variants. But to use either one of those things, we need to first draw, step one is always draw the free body diagram. So let's draw a free body diagram of this object. So that's point O, and maybe we have a couple of reaction forces in the x and y directions. We have the point C, which is downward. We have gravity at that point C, downward, and like I said, C is halfway between O and A, so that's L over 2, and we have the force F like so. Okay, now what do we want to do? So if you're asked to find angular acceleration, you want to think which equation has angular acceleration. And the equation that has angular acceleration is essentially the so-called Euler's equation, or the equation that relates sum of moments to something like I alpha. Okay, so let's recall what those equations are. Recall sum of moments about the center of mass is basically I about center of mass times alpha in the k direction. And then if you have if you want to take moments about a different point, sum of moments, let's say about point O, then it's equal to still sum of moments about center of mass alpha plus R C with respect to O cross M A C. Okay, so these are the two equations that are available to us, and we can see which one we want to use. Okay, which one to use? So let's call this equation 1, and let's call this equation number 2. By the way, this IC, moment of inertia of the pendulum about point C, if it is a uniform bar, so assume OA equals uniform bar, so that IC equals ML squared by 12. So let's say that's also given. Okay, so all this is given. So in any case, which one of these two equations to use? Well, if we used equation number 1, which is take moments about point C, well, we have these forces, the reaction forces, Rx and Ry, which will have a moment about point C, and those reaction forces are not known. And we don't really care to know them either, in some sense. We are not really asked to find an expression for the reaction forces, and we are told that the expression will not depend on the reaction forces. So if you take moments about point C, these reaction forces will appear here, and we don't really want them. So it may actually be better to take moments about this point, take moments about point O, so that the reaction forces which pass through that point O do not appear in the equation at all. And then we can write expressions for this, which just has to do with theta double dot, an expression for this, which will again depend on theta and so on. And we will have a relationship that involves the forces through essentially this moment expression, and the various theta and theta double dot terms through these terms. And we will have what we need, which is an expression for the angular acceleration. So let's actually try to use this equation. So what I was going to say was using 1 means that we will get terms involving Rx and Ry in our equations. To avoid solving for Rx and Ry, take moments about O, so that Rx and Ry have no moments about O. Okay, so use equation 2. Okay, so let's do that. let's take moments about point O. So what's moments about point O? We have, well, Rs and Ry, they're not going to have moments about point O. We're going to have mg, and you can, some of these things you can just write out the answer directly, or you can try to do the cross product to find the moments. So let's maybe go slow and try to take the moments carefully. Well, if you want to do sort of take the moments quickly, okay, mg is the force, r L over 2 cosine theta is the moment arm, right? So if you have a triangle like this, and this is point C, point O, point A, this is going to be basically L over 2 cosine theta, and this is going to be L sine theta, and we have a force mg acting here, and we have force F acting here. We are taking moments about point O, so oops. So sum of moments about point O is basically mg times L over 2 cosine theta in the clockwise direction, and clockwise direction is negative. So minus mg L over 2 cosine theta k, and it's always k, and whether it's positive or negative depends on whether it's anti-clockwise or clockwise. If it's anti-clockwise, it's negative. If it's clockwise, it's positive, right? So in this case, it's mg times L cosine theta, the perpendicular distance between the force and the point, and that's that. And for this force, it's going to be force times the perpendicular distance to the point, which is going to be L sine theta. But it's again a clockwise moment, so it's going to be minus F L sine theta k. So that's the left-hand side of this equation. What is the right-hand side? To get the right-hand side, we need IC, which is known to be ml squared over 12. Alpha is just theta double dot. And then we need to find these things, RC with respect to R cross MAC. So we need to compute other terms and sum of moments with respect to O equals IC alpha K plus R C with respect to O cross with M A C. Okay, so this we've already computed, and we said IC is just M L squared by 12. Alpha is just theta double dot, or we can find just alpha directly. RC with respect to O, what is that? That is a vector, right? So if you say this is the J direction, and this is the I direction, we have RC with respect to O is R cosine theta I sine theta J. So L over 2 cosine theta I, L over 2 sine theta J. Okay, so that's R C with respect to O. What is AC, the acceleration of the center of mass? Well, we want to express it in terms of these angles, okay, in terms of these angles, the acceleration of the center of mass. And you can use that using polar coordinates. Recall polar coordinates. So if you actually say this is point O, this is point C, and this is ER, and this is E theta, then acceleration of the center of mass is minus, and this thing is basically L over 2, which you can call R if you want. R theta dot square minus R theta dot square ER plus R theta double dot E theta is our old polar coordinates formula for acceleration. And you can just substitute R equals L over 2 to get this formula. Okay, so that's the acceleration. Let's plug everything into this equation. So let's call this equation 3. Let's call these things 4, 5, 6. Use 3. Well, before we, I guess, plug everything in, let's compute this cross product. Okay, let's compute that cross product before we plug things in. So RC with respect to O crossed with MAC, what is that? Okay, RC with respect to O, we've written it in this form in terms of I and J, but because we are going to take cross products with something written in polar coordinates, we might actually write this in polar coordinates more conveniently. So let's do that. So what is that? So R C with respect to O in polar coordinates is just L over 2 times ER, right? So it's just L over 2 times ER. Okay, so let's just write that out. L over 2 ER cross product with minus L over 2 theta dot square ER plus L over 2 theta double dot E theta. And if you take a cross product of ER with ER, that is going to be 0. So equals 0 plus we have L over 2 square. Taking cross product of this and this, you get theta double dot and ER crossed with E theta. ER crossed with E theta is just K. So we have theta double dot L over 2 square times K. Okay, so that's what this term is. This term just became, well, we dropped an M somewhere, so let's put the M there. M. Okay, so I think now we are ready to plug everything in. So let's plug everything in. Let me rewrite the equation. Sum of moments about O equals I alpha K, IC alpha K plus RC with respect to O cross MAC. And this thing we said was right here, minus mg L over 2 cosine theta minus f L over 2 sine theta, all in the k direction, equals IC, which is ml squared by 12 theta double dot k plus, and we just solve for this quantity, which is this quantity, m theta double dot L over 2 whole square k. Because we have a whole bunch of k's, we can cancel them all out. So what do we have? Here we can group terms here. You can say it's equal to theta double dot m L squared by 12 plus L squared by 4. If you do the simplification, you will notice that it's equal to m L squared by 3. So that's what we get on the right-hand side. The left-hand side is this. So what we have is theta double dot equals minus mg L over 2 cosine theta minus FL over 2 sine theta divided by m L squared by 3. So that's the answer. That's equal to alpha, the angular acceleration. Okay, so that's method 1. Method 2 is different. Method 2, one has to be careful applying this moment. It turns out because O is a point fixed on the rigid body, and in space, we can use sum of moments about O. Even though O is not the center of mass, we can use IO times alpha K. Okay? So as opposed to equation 3. Or was it equation 2? I guess equation 2, as opposed to equation 2. Okay, sum of moments about O is still the same. But what is IO? What is IO? IO is computed using what's called the parallel axis theorem. Is basically IC plus MOC square. So that's equal to M L squared by 12 plus M L over 2 whole square. And if we simplify that, we will actually get M L squared by 3. So that's going to be IO. So when you plug everything in to this equation, what shall we call this? Equation 7 or something. Plug in equation 7. We have exactly the same as before, mgl over 2 cosine theta minus FL over 2 sine theta. Those are the moments. Equals IO alpha, which is m L squared by 3 alpha. So alpha equals this whole thing, mg L over 2 cosine theta minus FL over 2 sine theta divided by ml squared over 3. Okay, and that's the answer is the exact same answer that we got here. And we were able to do that with this modified equation much more simply. But notice that this modified equation is true only in some special cases. This equation is true, of course, if O was the center of mass. In this case, O is not the center of mass. But it applies because O is a point fixed on the rigid body and in space like this. If it's fixed point, then we can take this simple relationship But otherwise, it turns out we have to use this more complex relationship. This more complex relationship is always true for any complicated system, however O is moving and so on. Okay, so let's stop there.